Okay, so this lesson is going to be the first case where we're going to look at what happens when you affect an equilibrium. So again, those of you that took biology, you would have talked about homeostasis and how changes in exercise, what you put in your body, whatever, affect the homeostasis or the equilibrium in your body. You may have talked about how this affects the environment in grade 9 or grade 10 science, ecology, and then climate change. Today we're going to look at what happens when you change chemical or factors that you can manipulate using chemistry. So we're going to do concentration, temperature, and pressure and volume. Okay? So when you have a reacting system and you have the product concentration increasing, then the reactants are being used to make the products, and so they are decreasing, which is the forward reaction. Once you have more products, they can start to collide, and then the product concentration would start to go down and the reactants would increase. We call this the reverse reaction. So today we're going to look at what happens when one of those directions is not equal. It is not the same anymore. And usually this occurs because we want the change to happen. We are stressing the system, and the system is going to have to reestablish its equilibrium state. Okay? So if you have a closed system that has the same color, pH, pressure, etc., then that would be considered at equilibrium. So tomorrow we are going to do the easiest one, which is concentration in our lab. We are going to change the concentration, and the procedure part takes like 10 minutes. The majority of the lab will be the analysis, analyzing what happened and why, what was the consequence. So today's 7.3 is just qualitative. Once we get to 7.5, then that's where we are going to, instead of just doing increase and decrease, we're going to say by how much. We're going to do quantitative changes. So again, this is sort of the introductory section for the first couple of weeks. And then what we're going to do is solubility equilibrium. So you're going to apply Le Chatelier's principle to say and look at whether precipitate forms. Then in the acid-base equilibrium section, you're going to talk about what happens when you stress a system using an acid or a base, and including proving it using math. So the next two lessons are essentially, they're really vital for the rest of the year. Okay? So we're going to start with concentration, which is the most direct sort of stress, and then we'll do temperature last, which requires the most brain power. Okay? So equilibrium is great until we want a different situation. Maybe you have a chemical factory and you're trying to sell the product. So that means that you need the system to shift to favor one side over the other in order to have a greater concentration. Some sort of disturbance has happened, some sort of stress has happened. What is the equilibrium going to do? So we can use Le Chatelier's principle. So a principle implies that this has been proven. And again, tomorrow we are going to do a very, very simple procedure, and you will show how this works. It's very straightforward. So we are going to predict how an equilibrium system will respond to a stress or disturbance. So if a stress has been brought upon a system, it's going to shift either forward or reverse or right or left. But again, if you don't like the terms right and left, you can think of forward as right and reverse as left. It's going to shift to minimize or offset the stress. So the system is going to adjust in order to oppose the change in order to reestablish equilibrium. So if you stay up all night, what does your body want to do? Sleep, right? It's the opposite of staying up all night. The same sort of thing can happen in a chemical system if equilibrium is possible. So what we're going to do, again, over the next week-ish, we are going to look at the system's initial equilibrium state, or I. And we've already sort of talked about this. When you have a concentration time graph and the concentration lines are plateaued, that is equilibrium. So initially equilibrium is established, and then something is going to happen, some sort of shift or change, which we're going to tomorrow or Thursday use the letter C for change. So it's being changed here and here, which are really obvious. And then right here is a little bit less obvious, but it's also the lines are no longer flat or plateaued. And the whole point is to get equilibrium again. So we want to reestablish equilibrium. So a change happens, and then the lines plateau. A change happens, the lines plateau. A change happens, and these lines would eventually be plateauing. Okay? So what we're going to do as we go through the note, there are plenty of different types of questions I could ask you about this. So the examples are a little bit different so that you get exposure to as many types of questions as you can. The next page in your booklet has the worksheet. So all of the questions are not the same. Please don't just do number 1 and be like, oh, I'm good, I got this. If you would like to do the best you possibly can, then you need to do as many of the questions as you possibly can, okay? Especially with this type of topic. Then Friday's quiz. This is the last lesson for Friday's quiz. So the next page after the worksheet, it says problem set number 1. So when we were online, I think I'm clever. Instead of calling it a quiz, I called it a problem set. So you can think of that like a practice quiz if you want to. The solutions are online, but I would save this till the end. I would actually save this until after Thursday's lesson. Don't even do it until right before the quiz. Try some of the other questions first, okay? We're going to do 3 types of stresses: concentration, pressure, volume, and temperature. And it sort of goes in order of the brain power required, okay? Concentration is the most direct. And then pressure, volume, there's a teeny little hitch to it, and then temperature requires the most brain power. So if concentration of a reactant or product increases, somebody has put in more product or reactant, you could do either, then the system is going to shift to use it up. So that's a direct opposing change. Increase concentration, what does it do? It has to decrease it. If you decrease the concentration, the equilibrium is going to shift to make more. So sometimes people will be like, Ms. Todd, that doesn't make any sense. Why would you decrease the concentration? But again, if you are trying to sell the product, then you could continuously take it out of your reaction vessel, and the system naturally would shift to make more. So again, the whole point to this is you are trying to get it to favor one side over the other because its natural state is balance, okay? So this example is already filled in for us. So the stress, sometimes you're told the stress, and then you have to talk about how it shifts. So the possible stress is adding more reactant. Sometimes a question will say, list the changes. When you have more than one reactant, like in this case, for example, if you said increase or add more CO or Cl2, because they're both reactants, that would be the same change. That would not get you 2 separate marks. Okay, so be careful there. So adding more reactant. So again, what is the system going to do? The equilibrium needs to consume the extra stuff that you have put in. Some people will think of it that way. You can think of this like if you have more reactant, then in order to get balance, that means you have to make more product. It's the same thing. That makes sense. It depends on how your brain works. Maybe you like the straight opposing change, increase it, then it needs to use it up. That's a direct opposite change. Maybe you rather think of it as balance. If you increase the reactant, that means you need to make more product. Either way works. So that means you need to make more product, or you need to consume the reactant. Some people will say shift away from the reactant. That's the same thing as well, which would be a shift to the right. You are shifting to the right, making more of this. If you shift to the left, you would be making more of these, which does not make sense because we've already put more in. The stress and the result have to be the opposite because you're trying to get back to balance. But if you don't like right and left, again, you can think of it like forward and reverse. That's fine too. You could even be fancy and go back to the rates unit. If you increase the concentration of reactant, that means that there are more reactants, which means you would get more collisions of reactant particles, increasing the rate of the forward reaction. That's fine too. All of those mean the same thing. And normally I don't ask questions where I make you explain the same thing 3 different ways. It would be more like, what's the shift, or this is the stress, and explain why, and you can pick whatever makes the most sense to you. Okay? So let's do a different example, okay? So now these 3 questions are all based on the same system, but they're all asked a little bit differently, again, to try to get you exposure to the different types of questions that you could be asked, okay? So I could tell you what's happening. So I'm increasing the concentration of the product. So you could say product, that's fine, or you could be more specific. So again, you would have to kind of make sure you read the question carefully, remembering that reactants are on the left and products are on the right, all that kind of stuff. Don't overcomplicate things, okay? So if you increase the concentration of a product, the system has to use it up. So this question only asks you for the shift. Sometimes what you can do is think about the why and then go back and think about the shift. You can predict what you think the shift would be, and then write the why and kind of check your work. You can do it that way too. So if the product concentration increases, which way would the system shift? If it shifts to the right or forward, you're going to make more of this. Is that what we want? No, because we increased it. So it has to shift in the direction where it is used up. So some people will think of it like shift away from the COCl2. That works. It will favor the side that does not produce COCl2, which is the left side. You can think of it that way. Or again, you can just straight up go, if you increase it, then the system has to use it up. Yes. So it's going to be left or reverse. The reverse direction does not make COCl2. If you decrease the concentration of CO or carbon monoxide, so again, this time now it's telling you a specific compound. So you would have to go look and check where it is. Okay, that's a reactant. It's being decreased or taken out or removed. So then what's the opposite of taking out? Increasing. So it has to, again, shift left or reverse because now it's being decreased and you need to make more. let's do this one. Okay, so now let's do number 3, where it's got, and we can explain a little bit more. So it's a different kind of question. So in this case, I've told you I want you to increase the yield of COCl2. So in order to get more COCl2, what shift would we want? Forward or reverse? Yes. So you could also, you could say like you want to shift towards the COCl2. That's fine, same thing. So this time I've just sort of told you the direction you want to go, and you need to decide how we're going to get there, okay? So with concentration, there's always increase and decrease. There's 2 choices. So it says list the concentration changes because there are 2 of them. It does not matter which one you think of first or write down first. That doesn't matter. Again, usually people are most okay with the increasing and then shifting away from it as opposed to removing the compound. It seems like, why would you do that to get more of it? But it actually, if a system if its natural state is balanced, then that it will work, okay? So again, we're kind of challenging the simple way that you've thought of reactions before. So how can we get it to shift to the right or shift forward? We're going to increase the reactants. So you can either write reactants or you could write CO or Cl2. All 3 of those are exactly the same and would only get you 1 mark, okay? All it says here is list, but to make sure your note is as complete as possible, let's write the Y, okay? So if you increase the reactants concentration, then it has to be decreased, which is shifting to the right. Or again, or you could say it has to shift away from the reactants. What's away from the reactants? Towards the products. That's a possibility. Or again, if you like to think of the balance, if you increase the reactants concentration, the balance would then be to increase the products. Okay, and then again, you could, if it bothers you to write decrease the concentration of COCl2, which would be fine, but you could write it more like removing COCl2, because then that makes a little bit more sense. If you take out the product, the system is going to shift to make more. Okay, so when you do concentration, because the graph we usually are using is concentration and time, then one of the things you can use, this can be used as a tool to help you visualize what's happening with the stress. So sometimes when I show students this, they're like, Ms. Todd, this is way too crazy. But really, this part is what you're used to. Reactant concentrations go down, product concentration goes up, equilibrium is established, and then obviously something at t equals 20 seconds, something is happening. So if you have a spike, you could have a spike up or spike down. So you're just looking here. What's happening to this? There is, at 20 seconds, there's a spike in the CO concentration, and it's an up spike or increase, right? It's like a normal graph. Up is increase in the Y. So what the graph can be used for is to, you could even think of it like checking your work, really. So forget about the graph for a second. If you increase the concentration of CO, what does the system have to do? It has to consume it, which means you need to decide which way it's going to go based on your thinking. Consuming it would be making more product or shift to the right. Shift away from the CO, which would be a shift to the right or forward. So any of those would work. So the graph should help us visualize that. So the spike occurs at 20 seconds, increasing the concentration of CO. Today, we're just saying increase, decrease. We're not going to really worry about by how much. That's what you'll be able to do starting Thursday. So increase the concentration of CO, which means that the opposite of increasing is we have to decrease the concentration of CO. So once it increases, does it start to go down? Yes. By default, if you decrease the CO by shifting to the right, then the Cl2 should also decrease. So the reactants happen to be the dotted lines. So the other reactant also starts to decrease. But it's not a spike because that's not the stress, just as an aside. If you shift to the right, we want to make more product to balance it out. Does the product line, which is solid, not dotted, does it start to increase? Yes, it does. Okay? So the graph is proving or consolidating the answer we just provided. And then again, equilibrium is established for a while because the lines plateau. 35-ish. As a stress is a little bit trickier. We'll save that for a second. I'm going to skip to 45 seconds. Okay? So this is a much more dramatic spike. So when we do the quantitative analysis, then this change would be a lot bigger than the spike at 20 seconds. But the basic shift is still the same Le Chatelier's principle, using it to predict. Okay, so at 45 seconds, what happened? This time, it's the solid line, which is the product. So increasing COCl2, which is the product. Oh, I guess I could write huge spike. So if you increase the product, then it has to consume the increased product. It has to shift away from the COCl2. You have to make more reactants to balance. So any of those explanations support a shift left or reverse. So all of these explanations are equivalent. And again, I wouldn't ask you to explain it three ways. So you pick what you like, okay? But let's check and see if the graph supports what we've said. So yes, there's a huge spike, increase at 45 seconds, increase the concentration of COCl2, which is the product. Then it has to be consumed. So it gets used up, it starts to dip. If it starts to decrease or shift to the left, that means that both reactants should start to increase. It's kind of hard to see because the CO line kind of crosses over, but that's okay. This one, the CO dotted line, starts to increase, and the Cl2 line also starts to increase. And again, if the graph kept going, the lines would have a period of plateau. So in a set amount or set interval of time, no matter how many stresses you add, the whole point is that the system wants to get back to the balance or the plateau, okay? The E for equilibrium. Pressure and volume and temperature, they can be shown as stresses on a concentration time graph, but it's a little bit trickier. So we're not going to focus on that this year, okay? Okay, so pressure and volume are slightly trickier because you do have to remember some ideas from grade 11 chemistry. So in grade 11 chemistry, we did a whole unit on gases. So you do need to check and make sure that your system is all gases, because even though we don't include solids and liquids at all, right? Even aqueous means dissolved in water. So to change the pressure of water requires a considerable amount of energy, which, that's not a natural thing. That's not going to happen. Whereas gases, it's very easy to change their pressure. So pressure and volume, they are an equivalent change. So again, or an equivalent stress. So if you are asked to list 3 ways, you can't say increase pressure and decrease volume if you want to get more than 1 mark. Okay, it would only be one change. I like to use in grade 11 the analogy, if you are gas particles in this big classroom, do you collide? Do you feel pressure from your gas particle classmates? No. So big volume, little pressure. If I tried to stick all of you gas particles under the cubby under the computer, little volume, would you start to feel pressure? Yes. Okay, so it's an inverse relationship. So increasing the volume means that the pressure is decreased. Just based on the type of stress, it's actually easier just to think of volume. So you don't even have to mention pressure at all, really. So if you increase the volume, that means that you have more space to fill up. So the equilibrium is going to shift to the side with more moles of gas. Okay? So the first things first, you need to check the states. Where are the gases? Are they all gases? Gas, gas, gas. Okay, we're good. Yes. How do you find how many moles of gas there are? You add the coefficients. So on the reactant side, for your notes, if you would like to emphasize, even though we don't usually write the 1, you can write them in if you like. Reactant side, 1 plus 1 is 2 moles of gas. Product side, 1 mole of gas. So the reactant side, does it have more or less moles? More? So if you increase the volume, it needs to shift to the side with more moles to fill up faster. So shift left. Okay. So someone in my other class showed me I forgot to change the pressure. So you guys, can you fix my typo? Decreasing volume increases the pressure. But again, you don't even really need to think about pressure at all if you don't want to. So if you shift to the side that has less moles of gas, then the decreased volume wants to be filled not as fast, or does not want to be filled. So again, how do you figure out how many moles? You just have to add the coefficients. So this is the same reaction, but we'll go through the same things again. Are they all gases? Gas, gas, gas. Yes, they are. The reactant side has 1 plus 1. The product side only has 1 mole of gas, so it has less. So a decrease in volume. How would it shift? I thought they were going to say right or forward. So pressure and volume really has less ways to sort of explain it or think about it than concentration, but you do have to remember more moles of gas, increase in volume, less moles of gas, decrease in volume. So you do have to remember that. If the moles of gas are the same on both sides, then there's no change. So generally speaking, a question like that is sort of kind of a trick. Why would I give that to you if I wanted you to list ways and you can't even use pressure volume? So usually, I can't speak for the homework, maybe there's one in there, but usually if I want you to use pressure and volume as one of the stressors, then one of the sides will have more moles and one of the sides will have less. Okay, so temperature requires the most brain power, and it requires you to remember some ideas from thermochemistry, okay? So the overall stress and the change or the shift are pretty straightforward. If you add energy or warm the system up, then it needs to cool it down. If you cool a system down, then it needs to warm up. Okay, so that part of it is straightforward. But you need to decide or look where the energy is. So if the system is cooled, it has to shift in the direction that produces energy. If the system is warmed up, then it has to shift away from the energy, or it has to shift in the direction that absorbs energy. So this can be, there's really sort of 4 possibilities here, and it can be difficult to keep them straight. So if energy is a product, that's exothermic, and delta H is negative. When you're given a delta H value separate from the equation, then I actually recommend that you rewrite it with energy as a product. So on the worksheet, number 2 has both types of questions where it's got energy is separate from the question, and then the energy value is already included, but it's harder to see if it's all by itself. But maybe you can do it, that's fine. But one of the strategies you can use is to write the energy in the equation, like a thermochemical equation. And then if it's endothermic, energy should be a reactant. If you're given the delta H value, it would be positive. So in this case, I've already given you the energy. It doesn't really matter how much it is. So it says here 10 kilojoules. It could just say kJ. It could just say energy. It doesn't really need to give you a value. That doesn't matter. Even when we do 7.5, it won't matter. So if the system is heated, then that means that the temperature has been increased, or the question could say energy has been added. So this example I've done both ways. How would it shift and why? And then also another type of question could be, once it shifted, which concentration would increase? This number 2, I'm telling you which direction to go, and you have to say what the stress would be. So it's, again, a different type of question. So when you do these questions, if you're given a stress and asked how it shifts and why, some people find it easier to do the why first and then predict the shift. You could also try to predict the shift, write the why, and see if you're correct. So there is a variety of ways to do this question. So if the system is heated, energy is added, the temperature is increased, then the system needs to cool down. Which maybe doesn't compute in your brain. The system needs to cool down. How does it do that? So you could think of it like the system needs to decrease the energy. Or if you are thinking about shifting away or towards, it needs to shift away from the energy. All of these are appropriate explanations for what would happen, okay? Or heat, doesn't matter. Same difference. Shift away from the kilojoules. So this is why a thermochemical equation where the energy value is actually in it already can be a better option than having the delta H separately. So here, this is exothermic because the energy is a product, but that doesn't really matter. You don't need to label it as exothermic, but we do need to think about if the system is heated, then it needs to shift away from the heat or it needs to cool down. So you look at where the energy is, it's a product. So if you shift forward or towards the product, you would make more energy, which is not the opposite of heating. We need to cool down or make less energy. So you want to shift to the side that doesn't have energy in it. Okay, so again, so we're going to look for the direction or the side of the equation that does not have energy. So what side does not have energy? The left or the right? The left. So if you heat the system up, it's going to shift left or reverse, because if you go this direction, you're not using any energy. You're not making any more energy. If you went to the right, you would make more kilojoules, which is not the opposite of making more. So this kind of question, it says, what substance's concentration could be increased or would be increased? So this is sort of the result of the shift. This is just a different way of asking what's happening here. So if the substance's concentration is increased by a shift to the left, you could write reactants, or you could write CO and Cl2. Both of those would be acceptable answers. So in number 2, now I'm telling you I want it to go forward or right. So what temperature stress should you apply? So again, you can still do this by thinking of the why first if you would like. So if we go to the right or forward, is energy on that side? On the right-hand side, or the forward direction? Yes, it is. So a shift forward or to the right, which is what I've told you I wanted, you're going to make more energy. Okay, so if you're making more energy, that's what's happening. Now we have to think of what the opposite is to be the stress. So if the system is making more energy, what did we do to stress it? We must have decreased its energy or made it colder. So again, you could have done this first and written the why and made sure it matched, or you can now read through your question and see if it works because you know this is right. I told you to do right or forward. Okay, so if I decrease the temperature, the system shifts to the right to make more energy, shifts to the right, we're good. Okay, so there are ways you can check your work or think about the logic of it. But this definitely is a topic where you have to be able to write your explanation. So I can't remember. Okay, so this is now a different system. So when you have to talk about energy right away, take a look at where the energy is. Energy is a reactant, so this is endothermic. But again, I'm not going to ask you to label it endo or exo. But if you would like to use that in your thinking, you certainly can do that. So this time it says that the system has been cooled. So again, it could say the temperature has decreased, energy has been removed, whatever. All of those are the same thing. So in this case, you decide how would you like to do this. I would like to write the why first and then think of the shift. I would like to think of the shift, then do the why and see if it matches. It really doesn't matter, okay? So if the system cools down, then what does it have to do? It has to warm up. So again, all three of those things mean the same thing. And you do not need to write all three when you're doing like a test or whatever. I recommend you write all three right now. But choose which way you like the best to think of it, okay? So the system has to warm up. That's the opposite of cooling. It needs to increase its energy because cooling means decrease in energy. or it needs to shift towards the energy. So, where is the energy? Is it on the left or on the right? Left, so it's going to be a shift left. So again, sometimes writing the Y first helps with figuring out the shift. This system is a little bit simpler. It says what substance's concentration would be increased. There's only one reactant this time, but you can write the formula N2O4, or you can still just write reactants, or reactant, I guess, in this case, and either of those, that would get you a mark, okay? Yes. So two things are different. The energy is a product, not a reactant, and the system is heated and not cooled. Okay, so again, temperature definitely requires the most amount of brain power. So take a look where the energy is and what stress is happening, okay? Because it is different if it's a product or reactant for the energy, and it's different when it's cooled or heated, okay? So now we're going to do the same type of thing. Oops. What is the temperature stress? But I'm going to keep going forward or right. So that's what I've told you to do. So take a look. On the right-hand side, is there energy? Over here, is there energy? No. So a shift forward or right, which I have told you to do, is it going to decrease or increase the energy? It's going to decrease. There's no energy there. Or energy is being decreased as a result of the shift, whichever way you like to think about it. It's not being produced. You're shifting away from the energy. Again, all of those things mean the same thing. But the question wants us to write the stress. So if the shift is decreasing the energy, what was the stress? It has to be the opposite. So if the stress is decreasing, or the result is decreasing energy, that means the stress must be an increase in energy. So again, in this kind of question, go the other way. So increasing, and check your work, increasing the energy, the system would have to shift away from the energy, which is forward. There's no energy on that side, which is to the right. Is that what I wanted? Yes. 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 Okay, and then the last slide, you might think, why are we even talking about this? But we have talked about a catalyst. Catalysts are just like with the rates unit, the reaction would start and end in the same spot, same enthalpy change, same overall reactants and products. So a catalyst is not considered a stress. It would just make the equilibrium happen faster. So a catalyst in general is a good thing for a reaction. And then this one here is really being a very particular chemist. But technically there are gases, which are called noble gases, that do not react. So then if you put a noble gas in an equilibrium, which would technically, normally gases would change the pressure and volume, because they don't react, there's no collisions, then they're not a stress, okay? So, you know, just maybe in the textbook there might be a persnickety question about noble gases. Just know that they're not a stress. Okay, so